Okay, the recording is live. The microphone is working. Uh, Today's class, Thursday, represents day 2 of a 2-day lecture on acids and bases. If you recall, on Tuesday's lecture, I had an issue with my iPad where the first half of the lecture was on board and the latter half, which was actual practice, was on the tablet. Now, I don't know if everyone got a chance to see the message on the Discord channel, but I was able to record independently a new lecture recording for Tuesday's material. I'm not actually going to play it, but I was able to re-record on my own time a new recording for that topic. So that, of course, means if the onboard lecture didn't quite mesh with you as well as the normal Zoom delivery does, then I was able to make a brand new lecture recording from my tablet. Now, of course, recognize that I wasn't really lecturing to anyone. I was just talking at my workstation. So the pacing is a little bit faster. In other words, this video actually isn't a full hour and 20-minute long video because there was no buffer periods like, hey guys, work on this for a couple minutes, or let's wait till we answer some questions. I think it's around like a 45 to 50-minute lecture. And one of the biggest reasons I do recommend that you watch this recording, whether or not you were in class on Tuesday, is because I go over different questions than what we did on Tuesday's class. So in addition to Tuesday's in-class problems and this new recording, there's a lot of new practice and thoughts you hear me go through as we work through particular questions. But before we get into today's day 2 topic of acids and bases, just a quick recap so we all understand if we're on the same page. In acids and bases, there are 3 primary topics that we'll go over. Of course, on Tuesday's class, we went over basic definitions, and we started to see a little bit of stoichiometry. Today, we will finish our discussion on acids and bases by talking about what is known as a titration that will lead into a pH curve discussion. Now, the fundamental thing to understand about acids and bases is that it all comes back to this definition of water up here in the middle in red. You see, historically, water has been known to exhibit both acidic and basic properties. It's one of the first earliest known examples of what's called an amphoteric substance. An amphoteric substance is one that is able to exhibit both acidic and basic properties. Over the course of history, various definitions have been put forward to define an acid and a base by various people. Initially, we had Arrhenius, who defined an acid as an H+ producer and a base as an OH producer. That logic makes sense based on the information they had available at that time, where again, water was both an acid and a base. It simultaneously produced hydrogens and OHs. Few years, maybe a decade or so later, Bronsted-Lowry devised a new definition. Although very similar in meaning, an acid is a H+ donor and a base is an H+ acceptor. Bronsted's big idea was that if a water is an acid and a base, if his definition holds true, then you should be able to just add a hydrogen to the H3O, to the H2O to form H3O+. Somewhat at the same time, contemporary in the realm of physics, another scientist, Lewis, defined an acid as an electron pair acceptor and an electron pair donor. It's important to understand that all of these definitions are true and interchangeable. In other words, an Arrhenius acid is also a Bronsted-Lowry acid, which is also a Lewis acid. It doesn't quite matter which term you use. If you're an acid, you're an acid. But for the purposes of Chem 300 and most chem courses that you will encounter, we will be referring to the Bronsted-Lowry definition, which is that acids are proton donors and bases are proton acceptors. We can use that logic to devise a generic acid-base reaction shown here on the bottom, a reaction between H2O and HCl. Now, the products of this reaction are shown here, H3O and Cl-. Now, I'd like to point something out. This reaction is not one that you could have predicted the products of. It does not nicely fit any one of the archetypes that we've looked at so far. So this is not the type of reaction I want you to expect, oh, I'm going to be asked to predict it. No, you will be given the entire reaction, and you may be asked to identify the acids and the bases present. Let's try to understand where these definitions come from. Just happening to start with H2O on the left, we see that we start H2O and we end up H3O+. Based on this, we can easily assume that the water has gained a hydrogen. That's what makes it a base. The beauty of acid-base is once you've identified one, you've also identified the other. So if water is a base, that means the other reactant must be the acid. We can apply the same logic to determine the acid and base on the product side. The only difference is we'll use that word conjugate, where the term conjugate literally means product side. So again, using H3O+, we see that it starts H3O and it ends H2O, aka having lost or donated a hydrogen. In this case, the H3O+ is an acid and it's labeled conjugate to make it clear it's on the product side. We can apply that same logic to various other types of reactions. Overall, what I want you to understand is that water has the ability to act as both an acid and a base, depending on the context. Now, throughout today's discussion, throughout even Tuesday's discussion, I did interchangeably refer to H+ as a proton. The reason for this is if we look at the standard hydrogen, straight off the periodic table, it has 1 electron, 1 proton, and 0 neutrons. H+ in the cationic form has lost its electron, still only has 1 proton, and has 0 neutrons. As a result, H+ is literally just a single proton. That's why the two terms are used interchangeably. That then led to our discussion on acid-base strength, in which we ranked acids by how easily they would donate that proton. And we showed what was called the pH scale. The pH scale down here is a numerical scale between 0 to 14 that allows us to rank or measure how well these acids are willing to donate a proton. From 0 to 14, smack dab in the center at pH 7, is described as a neutral solution. Anything to the left of 7 is described as acidic. Anything to the right of 7 is described as basic. Now, the pH scale is one of our most fundamental indicators that acidity and basicity is in fact a spectrum. In other words, to the far left, we have a very strong acid. To the far right, we have a very weak acid. But by the same code of logic, a strong acid is simultaneously a weak base. In that, these acid and base definitions are not binary. They're not one or the other. You are not either an acid or a base. Chances are you're both. You can just be a really good acid or a really good base. By the same code of logic over here on the right, a weak acid is simultaneously a strong base. The pH scale is very useful for this reason because it allows us to rank not just acids, but bases as well, such that even though we also have a pOH scale, it is not as commonly used, aka dropped out of the general lexicon. That's what then gave rise to our different calculation methods to calculating pH, 6 equations in total. These 6 equations in total are things that you are expected to know, use, and manipulate to solve various calculations related to pH, pOH, as well as the concentrations of H+ and OH-. I said this on Tuesday's class. I'll say it again today. You do not need to memorize these equations. They will be provided to you as part of the exam booklet on the reference sheet. And that pretty much goes over what we went over on Tuesday. And then we did just a couple questions from the worksheet. Like I said, I do encourage you to watch the new recording. I go over different questions than I did in lecture, so it offers additional practice and additional insight. Before I move on to today's topic, does anyone have any questions? Okay. Let's get it done. Now, from Tuesday's lecture, we learned the numerical quantitative way of ranking acids and bases, aka the pH scale. Today, what we want to know is if there are any other classical indicators for what is a strong acid, a weak acid, and similarly, a base. We're going to draw a long table like so. comparing both acids and bases. In other words, without specific pH numbers, without a specific metric, I do expect you to be able to know and identify various strong acids and bases based off of their chemical formula. This is all to say, a couple examples of strong acids include HCl, HBr, HI, HNO3, H2SO4, and HClO4. These up here in purple, just where they are on the table, are classic examples of strong acids. And they are examples I expect you to know and memorize. You will not be given this chart as part of the exam booklet. Now, one thing you may notice, at least in the first row right here, is that we have HCl, HBr, and HI. In other words, we have chlorine, bromine, and iodine, all halogens, aka in group 17. The only one I'm missing, of course, is HF, fluorine. However, this is not conventionally included in any discussions of acids and bases simply because it's too dangerous to work with in the lab setting. It usually requires special training or some sort of supervisor. So as a result, we try not to actively teach it as a useful acid. It is a strong acid, but it's simply too dangerous for us to actively talk about in our discussions in class. Some examples of weak acids include CH3COOH, H2CO3, H3PO4. Now, a common question that comes up is, how can we look at the formula? Let's say I give you a brand new formula and I ask you, is this strong or weak? Is there some sort of rhyme or reason that you can use? The simple truth is, in this level, you can't. At this level in Chem 300, I am expecting you to memorize this list. In other words, what I'm trying to say is I will not give you an acid not on this list. You may be wondering, well, can I go off of number of hydrogens? I notice all of the strong ones have either 1 or 2 hydrogens. That is fair. But technically, we have 2 hydrogens over here with H2CO3. So the logic falls apart right there in terms of having 2 as our cutoff. So it is, in fact, recommended that you just memorize this chart than trying to actively figure out rhyme or reason behind it. Those are acids. Bases, on the other hand, strong bases are traditionally group 1 or 2 hydroxides. What do I mean by that? I mean any metal from group 1, such as lithium with a hydroxide, or anything from group 2 with that same hydroxide. Here we have lithium and calcium hydroxide. Lithium is in group 1, calcium is in group 2. But traditionally speaking, a strong base is any hydroxide with something in group 1 or group 2. A weak base, some very common examples include NH3, ammonia, and most other metal hydroxides not in group 1 or 2. An example of this is aluminum hydroxide. Aluminum is in group 3. This is a metal hydroxide, not in group 1 or 2. This is a weak base. So in contrast to the acids, there is a rhyme or reason for the bases determining if something is strong or weak. And it's important to be able to know just very quickly what the differences are. Now, as we continue our discussion on pH, I do want to make a couple notes or observations about pH and pOH. Sure. Now, in general, some things that have been observed about this discussion of pH and acidity. Number one, pH and pOH are unitless. They do not have an associated unit. For example, what you would say, the pH of a human body, or average pH, or expected pH, or ideal pH, whatever, is around 7.3. No units associated with it. Also, for pH and pOH, it is common or convention to reduce to the first decimal place. AKA, we'd rather write 7.3 versus 7.31. It's convention to reduce it to the first decimal place. Next, we've talked about these terms before. Concentrated and dilute. This is stuff we talked about way back in our molarity chapter, or concentration chapter. The analogy we used was about lemonade. We add too much water, it's dilute. We add too much lemon juice and sugar, it's concentrated. It's important to understand that these terms do not necessarily translate to a strong or weak acid. These terms, concentrated and dilute, simply just refer to the ratio of stuff to solution. What I mean by this is a dilute solution, again, dilute meaning lots of water, of HCl is more acidic than a concentrated solution of NH3. Remember, we know from the previous chart, HCl is a strong acid, NH3 is a weak base. So this chart reigns supreme regardless of whether or not that this solution is described as dilute or concentrated. Again, the terms dilute and concentrate just refer to ratios. It's the amount of stuff versus the amount of solution. Great. Now let's talk about an experimental technique called titrations. A titration experiment, or a titration reaction, is one in which you add a solution of known concentration to a solution of unknown concentration. You are adding a solution of known concentration to a solution of unknown concentration. These terms should trigger a memory for you. At least one specific memory starts with R, ends with ODMAP. Titrations represent one of the most popular type of experiment in which stoichiometry is used. It is specifically measured or tracked via pH changes which is indicated by color changes. All right, so it says it's measured by pH changes. We know what pH is. pH is a quantitative metric. It is a measure of how strong an acid is. So let's take a look at a very simple example. Here we have the reaction between sodium hydroxide and HCl. This is one maybe you may already be able to predict in your head. Double displacement. This, of course, tells us it'll be sodium chloride added to water. Now let's talk a little bit more about where this pH change comes from. What exactly are we measuring? What exactly are we tracking? So the HCl, our acid, is under 7. It's less than 7. This is our acid. Sodium hydroxide, we have here a hydroxide, and sodium is in group 1. So we have here a strong base. So we will say the pH is greater than 7. As we add these two together, of course, as we've come to expect both in lab and in class, the molecules will react. Ions will switch, crisscross, blah, blah, blah. Stuff we've already talked about. We know how we get to the products. But what's important to understand is that when we have two differing pHs, eventually it will equilibrate. Just as how if you had a hot object and a cold object and make them touch, eventually they will equilibrate to a moderate medium temperature. By the end of the reaction, when we form water, we are expecting a neutral solution. A pH of 7. Please note that right here, this is a slightly equal sign. It's not a straight equal sign. It has a little squiggle on top to make it clear that it's close to 7. Sometimes could be perfectly 7, but it's approximately 7. So looking at the individual pHs of the chemicals, we can track how the pH should change. We have here a basic solution, we have here an acidic solution, and by the end, we are neutral. So how this setup looks is you're going to have your flask. I'm going to do a little drawing first, so just give me a second. Okay. So in this flask down here on the bottom, we have our HCl. We know the volume of HCl in the flask. And as of right now, we don't know the concentration specifically. So we know the volume, what we don't know is the concentration. For the purposes of this example, let's put an easy number. Let's say that we're dealing with 25 mils of HCl. We know the volume. What we don't know is the concentration. This is our flask on the bottom. Over here on the right, we have our ring stand. We've seen that in lab the last couple of weeks when we use the Bunsen burner. So we should at least have a physical idea of what this setup looks like, just something connected on top. And this right here is what's known as a burette. In the burette is our sodium hydroxide. And as of right now, we do know the volume. And we also know the concentration. Make it easy. Let me just color code everything. Okay. Let's say for the purposes of this example, 22.5 milliliters, and the concentration is 0.0982 molarity. So we have our setup. We have our acid in the flask. We have our base in the burette. And of course, what the idea is that we will simply add the base to the acid. Recognize that in this flask right now, the pH is less than 7. In the flask with just HCl, just our acid, it's less than 7. But as we continue to add base to our acid, do we expect the pH in here to decrease, or do we expect it to increase? Increase. We've talked about this where by the end of the reaction, we are expecting a pH of around 7. So if we start initially less than 7, of course, we're moving towards 7, we're increasing. So by the end of the reaction, the pH in the flask increases. Now that we understand physically how this experiment is set up. Yep. Okay. Sorry, where was I? Okay. By the end of the reaction, the pH in the flask increases. That's okay. I told you that it's marked by color changes. By the end of the reaction, we end up with a faint pink color. So the idea of titration is that we are reacting an acid and a base, knowing that we're going to form water, recognizing we have a visual indicator when the reaction is done, the color changes. And when the reaction is done, we get the following values. We know how much of each we have. We know in the flask is 25 mils. As we add base to the reaction to the flask, we end up adding 22.5 milliliters. How do we use this information? To find the concentration of HCl. Well, that part's actually easy. Because if I were to rewrite this once again, we know we have some information on sodium hydroxide. Whoops. And we're trying to find information about HCl. So we know in some way, shape, or form, we're going to use the roadmap. We can draw in our roadmap, fill in our bus passes, and label it. Molar mass, molarity, mass, moles, volume, and ratio. So we've performed the titration. We have reacted the two. We have seen how the pH changes. We've seen the faint pink arise. From the titration, we know some information. From the previous page, I did tell you the concentration of sodium hydroxide was 0.0982. I also told you that we were dealing with 22.5 milliliters. In the case of HCl, we don't know the molarity, but we do know that we have 25 mils of it. We're going to put these values in appropriately. HCl, 0.025 liters. Remember, we have to convert to liters in the roadmap. We have to divide by 1,000. 0.0225 for the sodium hydroxide. Yet again, we have to convert the volume to liters, divide by 1,000. We know the molarity that was given to us in the question, 0.982 molarity. And what we're being asked to find is the molarity of HCl. Yes. 0.092. Thank you. 0.0982. Thanks, William. The roadmap ahead tells us what to do. Volume to moles, mole ratio, moles to molarity. It's kind of tidying this up. We'll just remove that top half to make it simpler on us. And we just solve it in order. First, we're going to get volume to moles of sodium hydroxide. N is equal to molarity times volume. Molarity is 0.0982. Volume is 0.0225. We put this into our calculator, 0.0982 multiplied by 0.0225. Looks like we get a pretty small number. Let's at least try to get 2 digits. So 0.0022. Let me just make sure I wrote that correctly. Yeah, 2 is, I think, fine, just for the purposes of this scratch work. Whoops. Next up is the ratio. We already have the equation over here. Quickly confirm for ourselves that it's balanced. 1 sodium, 1 sodium. 1 OH, 1 hydrogen, 1 water. 1 chlorine, 1 chlorine. So the ratio is, in fact, 1 to 1. So 0.0022. It's the exact same number, 0.0022. The last step is to go from number of moles to molarity. Specifically for the HCl, where molarity is equal to number of moles over volume. We just calculated the number of moles, 0.022. And we previously knew the volume, 0.025. That's how you do it. There we go. Okay. 0.025. Oh, whoops. Should not have did it like that. Divided by 0.025. Looks like our final answer is approximately 0.088 molar. So this part should be recognizable. You have some information about one chemical and you're being asked information about another chemical. This part is the part we're used to. It's the actual experiment that we're teaching today, that we're learning about today. Because in a couple weeks, you're going to do an experiment just like this. And you're going to perform the experiment. You're going to watch the color change. You're going to carry out these calculations. But I want you to understand that titration is just the experiment, but the actual calculations and theory is the stoichiometry you know oh so well. Do we have any questions so far? Okay. So this is an immediate benefit of titration. The questions that we've done in class, stoichiometry, how much of this do we need to react with that? What mass is required? What mass is produced? All of that is just theoretical calculations. Titrations is the actual in-lab experiment. So what else can these experiments tell us? In short, they tell us about pH curves. Now, on the previous page, what we did, or at least the previous pages, is that we talked about how the pH changes as a result of opposite ends coming together, trying to equilibrate. And we know, based on the experimental setup, that the base is added to the acid. So we can actually draw a graph measuring the volume of base added against the pH that we see. In the case of a strong acid, strong base combination, what we see is that the curve starts really, really low. Remember what's in the flask. The flask is the acid. Acids are less than pH 7, and I've told you in this case this is a strong acid, so we're very, very low. I've just put 2 just to arbitrarily pick. You could have picked 1, you could have picked half. If we track how this pH changes and sort of arbitrarily put 7 and 14, it's not perfectly drawn to scale, but at least gives us an idea of what we're working with. The graph we see looks something like this. An S-shaped curve. An S-shaped curve that starts around pH 2 and continues to rise until it sort of levels off around a pH of 14. Think about this, and this should make intuitive sense to you. In the flask is our acid Our acid, our very strong acid, is around pH 2. As we add a base to it, the pH increases. Eventually, the pH increases to approximately 7. It is at this point in the reaction that we see that faint pink solution. This is what's known as an equivalence point. As per the graph, we know when the reaction is done when the pH is around 7. It's actually the steepest part of the curve. The reason the pH continues to increase, however, is because in theory, we would continue adding bases. We know the reaction stops, but we're just going to keep adding a base. So the very strong acid starts out at a low pH, pH 2. And by the time the reaction finishes, we end up with a very strong basic solution. We can draw a graph like this for basically every type of combination. If we again plot volume of base added versus the change in pH, and as best as we can, put a slight scale here, but this time looking at a weak acid and a strong base. Let's talk through this. In the flask is our acid. We know we're starting under a pH of 7, but we're specifically dealing with a weak acid. A weak acid actually starts somewhere closer to 7. And as we add base, the curve will appear till eventually it levels off. Where yet again, we do see that equivalence point, that end point, in that very steep region. Not perfectly 7, but pretty damn close to it. Notice the difference in graphs. Similarly, notice their similarities. They both take on this S-shaped curve. The difference, of course, is the scope, the magnitude. When we had a strong acid, we started really, really low. When we had a weak acid, we were still under 7, but we weren't that low. If it helps, you can even write this as 5. And why did we keep going all the way to pH 14? Because we had a strong base. Let's try another one. This time, we will react a strong acid and a weak base. All right, so this is the first time we're dealing with a weak base. We've been dealing with strong bases before. This time we're dealing with a weak base. Let's take a second. pH, volume of base added. Arbitrarily just putting some things on the scale. 2, 7, 14. Okay. I'm going to look for answers, so someone shout it out now. We're starting with a strong acid. Should I start at A, B, or C for the strong acid? C, right? We're dealing with a strong acid. So I know I'm going to start down there. Weak base, we know where we're going to end up. Try it now. Do we end up at A, B, or C? C7, we're talking about a weak base. So B, remember, strong base is what ends at 14. We're not dealing with a strong base, so we're just right under it. So it looks something like this, where yet again, we see our equivalence point may not be perfectly 7, but it's pretty damn close to it. Now we're going to draw the last graph. I'd like you all to take a stab at it yourself first. We're drawing a graph that shows the titration between a weak acid and a weak base. Try to draw what you think this graph looks like yourself first, and then I will show you what it actually looks like. Take about 2 minutes. See, we know what the general shape is. It's a general S curve. It's the magnitude that we're looking at. Think about what we're dealing with. We're dealing with a weak acid. So we're starting weak acid and we end up weak base. All right. Hopefully we have the same answer. Weak acid starts high, ends low. It doesn't go all the way down to 2. It doesn't go all the way up to 14. And yet again, our equivalence point, that steepest part of the curve, is right by 7. So it's important to note and understand when we're dealing with strong or weak and how that necessarily affects the pH. Hopefully everyone brought the problem set from last class. I don't have any extra copies on me. If you don't have a copy right now, it's okay. I will project it on the board. Let's do a couple of questions from the very last problem, problem 4. Problem 4 simply states, sketch titration curves for the following scenarios. We've done a lot of sodium hydroxide and HCl so far, so let's actually skip that one. Let's do part B first. We're told that we're reacting 40 mils of NH3 and CH3COOH. We know generally what a titration curve will look like, so we can draw those pieces out, even if we haven't filled it in just yet. We know that the x-axis is the volume of base added. And we know that the y-axis is pH. Similarly, what we can do straight off the bat, maybe not perfectly drawn to scale, but as best as we can, just draw in our pH values so we know our scope and what we're dealing with. It doesn't need to be perfectly drawn to scale, but just some numbers there so we orient. Now the question is, what pH do we start at? What pH do we end at? To understand that, of course, we have to ask ourselves, are we dealing with a strong or a weak acid? Are we dealing with a strong or a weak base? Here's how we know that. That chart from the very beginning of today's lecture. This is why it's so important to memorize the chart, because it allows us to make very quick claims and statements about acids and bases that, of course, will clearly help us predict strong and weak. So we're looking for NH3 and CH3COOH. Looking at our chart, NH3 is a weak base. CH3COOH is a weak acid. That is how we know for this titration curve, we are dealing with a weak acid and a weak base. We know that in the flask is our acid, so we know we're starting low. We're dealing with a weak acid. Let's arbitrarily put it, I don't know, let's say right here, closer to 7 than 2. We're also dealing with a weak base, so we're not going to get that close to the 14. So I just draw in these purple lines to sort of help me understand where are my limits. And when I'm drawing, I like to take just a quick second. I like to just draw some dotted straight lines. Again, it just helps me understand where my upper and lower limits are. I know what my graph should look like. It should look like an S curve, like so. And now that I've nicely drawn it out, I can just erase the dotted lines. This right here is in fact the answer to part B. It is just a sketch of the curve. Remember, by nature of the word sketch, it's not perfectly drawn to scale. It's just as best as we can, a visual estimate. If I ever ask you such a question on an exam, here are where the points are coming from. You get 1 point for that S shape. You get 1 point for the correct starting point, aka if it's a weak acid, you've chosen somewhere close to 2. If I ask you to do a weak acid and you start down here, that's immediately wrong. You also need to have a correct end. Weak base means not as high as 14. And then finally, we need that steepest part around 7. Doesn't need to be perfectly at 7, but as long as that steep range is close to 7, that's good. And then there's 1 more point for correct labeling of units, aka label axes, sorry. So this graph represents a 5-point question where you're ultimately just being asked to sketch a graph. Yes. 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 As you progress further into chemistry, Chem 400 and onward, these axes will change. But Chem 300, we're limiting it to this. I would like everyone to try on their own right now, part C. Please notice, even though I didn't mention volume, the volume itself, the 40 mils, did not appear in the overall graph. It's just there. It's not necessary to include in any way, shape, or form. Please sketch the titration curve for part C, and then we'll do it together. Remember that for all your graphs, the axes are the same, pH and volume. You should be able to draw those axes without thinking too much about the question, because those are going to be the same. You then look at the question to identify strong and weak. All right, I see a lot of pens down. Let's look at it. So here I've drawn just the starting layout of the graph. Like I said, the graph should stay consistent with whichever question you're working with. I have just drawn as best as I can to somewhat of a scale to 2, 7, and 14. Now we're going to look at the individual chemicals. KOH is an example of a group 1 hydroxide. Potassium K is in group 1. So we have here a strong base, SB. HNO3, one of our examples over here, is an example of a strong acid, SA. Now that we have our pieces together, we're just going to map it out. We know that our strong acid will start low. We know that our strong base will end high. I like drawing those dashed lines because it gives me an easy way to draw. Then I'm going to draw my S curve with that steepest part being near 7. And then I will erase the dotted lines just to increase clarity. Do we have any questions from part C? Okay. I now like to talk about part D. So let's erase some of these pieces so far. That way I'll just need to draw it back, no problem. Okay. Looking at part D as in dog, we're dealing with sodium hydroxide. Sodium is in group 1. So we're dealing with a group 1 hydroxide. That is a strong base, SB for short. Now we have HCOOH, which if you notice, isn't exactly present in the charts. So how do we know what it falls under, strong or weak? Well, the answer is you are at the point where you are expected and able to make an educated guess. HCOOH may not be explicitly present in the chart, but something that looks a lot like it is in the weak acid section. Look at the difference. We have a CH3 here versus a hydrogen. Otherwise, they're both identical. They have the COOH. What this allows us to do is it allows us to make an educated guess. They may not be identical, but they're just similar enough that we can say HCOOH is a weak acid. So the chart, as simplistic as it is, as short as it is, not only allows us to identify strong and weak acids, but it allows us to identify or make educated guesses. For example, we see here we have HNO3. NO3, that's a nitrate. That's one of those polyatomic ions. Don't forget there is another polyatomic ion like this that is NO2 minus. That's nitrite. So where do you think HNO2 will end up? In the strong acid section. All right. Let's draw in the chart now. We're dealing with a weak acid. So we're going to be close to 7. May not be perfectly 7, but pretty damn close to it. We have a strong base, so we know we're going to end up at 14. Drawing those dashed lines to help us draw the curve. Then we're going to connect it with that steepest point being close to 7. I see your hand. What's up?
The exam, do you have pH and volume with base added?
Yes, on the exam, I would ask you the question exactly as sketch the titration curve, and you would be expected to draw the labels, draw everything for the 5 points total. As of right now, I do not see myself giving you a template to label. I would ask you, here's empty white space on the paper, draw the graph. It's a good question. Any other questions on this? Yes, Andrew. Yes, I will not be providing you with this chart on the exam. You are expected to commit this to memory. Like I said, you could figure out rhyme or reason to identify, and you probably could find a suitable explanation or rationale, but I do think it's easier to use like flashcards or Quizlet to just memorize them. As you do more and more practice, they become a little bit easier to remember, just like the periodic table. Any other questions? Yes. Yes. Okay. That ends our discussion on acids and bases. With this problem set, let me be sure to tell you what your extra credit is. On the first page, it is any 5 rows. So the extra credit from the first page is any 5 rows. Between Tuesday's lecture and the recording, I think I've done like the first 5 or 6, so anyone after that. Second page is practice. Problem 2. Any 3 questions. Between class and the new recording, I believe I did the first 4. Anything after those 3. From problem 3, any 2 questions. And from problem 4, any 3 questions? We're going to end lecture for today. We do have a wet lab tomorrow. Please come dressed appropriately for lab. Otherwise, I cannot allow you to conduct the experiment. Have a good day. I'll see you all tomorrow. If there are any questions, come talk to me now. Wet lab tomorrow, wet lab.